Hi dear students. So in our last video we discussed few concepts related to the potential energy. So we derived the expression for gravitational potential energy. We came to know the conservation of this gravitational potential energy in case of the freely falling body under gravity, and we discussed the concepts of elastic potential energy, and we came to know how the elastic potential energy is conserved in case of the stretching of a spring or compression of a spring. That is the conservation of elastic potential energy in case of a spring, loaded spring, isn't it? And let us continue our discussions related to the concepts of the work, energy and power, and today we are going to learn the concepts related to power. So what do you mean by power? If you are going to consider this work, energy and power, almost they seems to have same kind of general meaning, but in particular all are different from each other, isn't it? So power, it is also associated with work done. So for doing work we require some energy. So power is nothing but the amount of work done with respect to time. By keeping the factor time, we are going to measure how fastly we are doing that work, how fastly we are completing that work. That decides the power of a person. So it is very simple. The power, we can define the power as power. It is symbolically written with letter P. The time rate of work done, the time rate of work done, that is nothing but power. Let us consider the example. So here we have two persons, person A and person B. We are allotting some task for both the persons that they have to run 100 meters. So both the persons A and B, they have been assigned with some work. They have to run, that means they have to do some work. So they have to cover a distance of 100 meters. Let us consider the person A takes 15 seconds and person B takes 20 seconds. So both are completing the task, both are doing the work, no doubt about that. But the person A is doing the given task in 15 seconds, and for completing the same task, person B is taking 20 seconds. So if we think of the power of A, that is PA, and power of B, that is PB, obviously we are going to say the first person has more power than second person. Even though they are doing the same work, but that work will be completed by the first person quickly within 15 seconds. He is completing that work by 20 seconds. So we can say power of A is greater than power of second person, that is person B. So how we are going to define power? Power is nothing but time rate of work done. Work done with respect to time. So P is equals to W by T. P is equals to W by T, where W is the work done and T is the time taken. And now we have to consider the forms of the power. That means we have to define the average power and we have to know about the instantaneous power. So let us focus on that. That is the average power and instantaneous power. So average power is nothing but the total work done divided by the total time taken. So simply we can write that average power P is equals to W by T only, where W is the total amount of work done during the total time interval, that is T. So that gives the average power. Then instantaneous power. That means, so let us assign our work to a person A. That means he has to complete 5 rounds. So he has to run across the circular path and he has to complete 5 rounds. So we are not waiting until the task has to complete. At some instant I want to know his power. For that we have to think of instantaneous power. Instantaneous power. The power at any given instant of time is called instantaneous power. We are not waiting until the completion of the work. So the instantaneous power can be obtained by some limiting condition, that is limit delta t tends to 0, that is delta w by delta t. It is called dw by dt. This is nothing but the instantaneous power. So still he has been completed only one round. His task is to complete 5 rounds. That means still the task has not been completed, but after one round we want to know his power. So now it won't be an average power. It will be instantaneous power. What is his power after completion of one round? That is at that instant, what is his power? So to get that instantaneous power, we have to consider the small work done by that person. That means he has still completed only one round and the time taken. So we are going to think that first round has been completed. That means we are applying the limit delta t tends to 0. That means we are considering for completing the one round the time we are just going to measure that one. That means we are not considering that delta t is continuously varying. So we are applying that limit delta t tends to 0, delta w by delta t, that is nothing but dw by dt, rate of change of work done with respect to time. That is time rate of work done is called instantaneous power. Almost whether it is average power, instantaneous power, everything is nothing but measurement of work with respect to time. If you are completing the work and if you are calculating that for the total time taken, it becomes average power. But at some instant we want to know the power, it will become instantaneous power. So in general we can define work done by time taken, that is time rate of work done is called power. Let us move on to the SI rate of the power. So the power they are defining as work done by time taken, that is joule per second, is called watt. So the SI unit of power is watt. So now we have to define 1 watt. The power is said to be 1 watt if 1 joule of work is done by a force in 1 second. Because of application of some force, the work is completed. That means if 1 joule of work is completed in 1 second, then the power is said to be 1 watt. The power is said to be 1 watt if 1 joule of work is done in 1 second. So now we have to think of the other practical units of the power. So we are going to make use of 1 kilowatt, that is nothing but 10 power plus 3 watt. We are going to measure the electrical energy in terms of kilowatt hour. Kilowatt hour is nothing but 3.6 into 10 to the power of plus 6 joules, because then we are going to consider kilowatt hour. Kilo stands for 1000, that is 10 power plus 3. Watt is nothing but 1 joule by 1 second, and hour is nothing but 3600 seconds. So second we get cancel. 3600 into 1000, it is nothing but 3.6 into 10 to the power of plus 6 joules. So 1 kilowatt hour is equals to 3.6 into 10 to the power of plus 6 joules. In the same way, we are going to make use of some higher practical unit of the power, that is horsepower. So 1 HP is equals to 746 watts. 1 horsepower is equals to 746 watts. So like this, we are going to make use of the assignments as well as some other practical units for the measurement of the power. So now the power can also be measured as, so power is equals to work done by time. We know that work done is equals to force into displacement. Therefore, the power is equals to work done can be written as force into displacement by time. If we are applying the uniform force, that means the force is not at all changing, then this force is constant. Displacement by time is called velocity. So power can also be written as P is equals to F dot V. Power is a dot product of force and velocity, where force is a vector, velocity is a vector. The dot product of two vectors will be a scalar. So the vector form of representation of the power, P is equals to vector F dot vector V. This can also be written as P is equals to F cos theta into V, where this can be understood by getting the expression of work. Work is equals to F cos theta into S. Isn't it? It is component of force along the direction of the displacement, like that. The component of force along the direction of velocity, that is called F cos theta. So P is equals to F cos theta into V. So this is all about the units we are using for measurement of power. So now next to the concepts of power and its SI unit, we have to move on to the concepts of collision. What is collision? See, if the object is moving, in its path if there is another object, so this moving object is going to hit the first object. So they are going to interact with each other. They are going to interact with each other. There is a physical contact between the two. Because of that, they are going to exert force on each other, and this interaction is called collision. This interaction between any two particles is considered to be the collision. So the collision is the physical interaction between the two objects, because of which they are going to exert force on each other, and we are going to have the types of collisions, that is elastic collision and inelastic collision. We have to consider. Collision is going to occur if the two bodies physically strikes with respect to each other. That means if the path of the one particle will be affected by the other, then they are going to interact physically. Because of this interaction, they are going to exert force on each other, and we are considering this as a collision. Collision is said to take place if the two bodies physically strike with each other, or if the path of one object is affected by the other, then collision takes place. So let us consider there is a body of mass m1 which is moving in some direction with velocity v1. So we have a body of mass m1 which is moving with velocity v1 in some direction. So here we have some another body m2 which may be in motion or it may be in rest. So let us consider it is at rest. So this body of mass m1 which is moving in a particular direction will go and hit the second body. Will go and hit the second body. So there is the physical contact between them. That means they are physically striking with each other. So because of that, there will be exchange of forces. That means they are going to exert force on each other, and this is called collision. This is called collision. So here in collision, we have to think of momentum and kinetic energy. We have to think of momentum and kinetic energy. If the collision in which both the momentum and kinetic energy are conserved, it is called elastic collision. A collision in which both the momentum and kinetic energy are conserved, then it is called elastic collision. And in each and every collision there is a conservation of momentum takes place, but whether the kinetic energy is conserved or not, that decides the types of collision. If along with momentum the kinetic energy is also conserved, it is called elastic collision. So in some interactions or in some collisions, only momentum is conserved but kinetic energy is not conserved, such collisions are said to be inelastic. Inelastic collision. So for elastic collision, both the momentum and kinetic energy are said to be conserved. Conserved means before collision and after the collision, if we measure the momentum, it must be same. In the same way, before the collision and after the collision, if we measure the kinetic energy, it must be same. Then we can say the kinetic energy is conserved. If both parameters are conserved, then it is called elastic collision. In the collision, only momentum is conserved but kinetic energy is not conserved. Such collisions are said to be inelastic collision. So we have two kinds of collision, elastic collision and inelastic collision. Elastic collision is one in which both the conservation of momentum and kinetic energy will take place. For example, the collision between subatomic particles, collision between atomic particles, collision between gas molecules, collision between two billiard balls, collision between two rubber balls. All these are examples for elastic collision. Let us consider the example of the collision of rubber balls. Let us have a one rubber ball at rest, the another rubber ball is going to strike the first rubber ball. That means it is going to hit the first rubber ball, and after collision they starts to move in some directions. So if we measure the momentum before collision and momentum after collision, it becomes same, and if we measure the kinetic energy before collision and after collision, it will also become same. So how the kinetic energy becomes the same? That means initially it is moving with some greater speed. Once it is going to collide, some of its kinetic energy will get transferred because the second body is also in motion. So the total kinetic energy before collision will be equal to the total kinetic energy after collision. That means whatever the kinetic energy we have initially, now after collision, both are moving but they are moving with some less velocity. So if we measure the velocities after collision and if we calculate the momentum after collision, which will be same as the momentum before collision. So in case of inelastic collision, why the kinetic energy is not conserved means, let us consider the collision of mud ball with wall. So if we throw a mud ball onto the wall, when it strikes, the mud ball will completely get deformed. ಆ ಮಣ್ಣಿಂದ ಮಾಡಿರುವಂತಹ ಬಾಲ್ ನ ಗೋಡೆಗೆ ಎಸೆದ್ರೆ ಅದು ಪುನಃ ಬೌನ್ಸ್ ಬ್ಯಾಕ್ ಆಗಿ ಬರೋದಿಲ್ಲ. ಈಗ ರಬ್ಬರ್ ಬಾಲ್ ನಾವು ಗೋಡೆಗೆ ಎಸೆದ್ರೆ ಅದು ಬೌನ್ಸ್ ಬ್ಯಾಕ್ ಆಗಿ ಬರುತ್ತೆ. ಮಣ್ಣಿಂದ ಮಾಡಿದಂತಹ ಬಾಲ್ ನ ಗೋಡೆಗೆ ಎಸೆದ್ರೆ it won't bounce back. Instead of what happens, the mud ball will get deformed. That means the kinetic energy gets converted to other forms of energy. Kinetic energy is lost, but the total energy must be always conserved. This kinetic energy may be converted into other forms. Hence, in case of inelastic collision, there is loss of kinetic energy, and that loss of kinetic energy will be obtained in terms of the other forms of energy, such as the sound energy. There may be production of heat it takes, whatever it may be. If the kinetic energy is not conserved, then we have to call such kind of collision as a inelastic collision. So we have elastic collision and inelastic collision. So collision occurs when there is a physical striking of the bodies takes place. If the path of one is affected by the second and they are going to interact with each other, that is called collision. We have elastic and inelastic collision based on the parameters, that is the momentum and kinetic energy, whether they are conserved or not. In case of elastic collision, both the momentum and kinetic energy were conserved. In case of inelastic collision, only there is a conservation of momentum takes place, but kinetic energy is not conserved. Yes. So after knowing about elastic collision and inelastic collision, we have to think of one more kind of collision, that is perfectly inelastic collision. What happens in this perfectly inelastic collision means, after collision, the two bodies or the two objects will stick to each other and they will move as a single object. Hence, we can't able to measure the kinetic energies of the individual objects. Hence, we can say this is the case takes place when there is a perfectly inelastic collision. So let us consider there is a wooden box and there is a bullet. So the bullet is moving towards or fired towards the wooden box. So it is going to enter the wooden box. Once if the bullet enters the wooden box, we can't able to observe the bullet, only we are observing the wooden box. So this wooden box may move, this wooden box may be at rest. The bullet inside the wooden box may cover some distance, or it may come to rest when it enters the wooden box. There is no clarity. Such kind of collision is considered to be perfectly inelastic collision. The collision in which after colliding the two objects will stick together and move as a single object. That is perfectly inelastic collision. And now we have to move on to the concepts of collision in one dimension and collision in two dimensions. So the very important thing we must know about the elastic, inelastic collisions, and we know about the perfectly inelastic collision. Yes. So now we have to derive one of the very important question, that is the collision in one dimension. What happens to the final velocities of the initial body and that is first body and the second body. So we have to consider the elastic collision, and we have collision based on the dimensions. So elastic collision in one dimension and elastic collision in two dimensions. Okay. So now collision in one dimension. What is collision in one dimension? What is this one dimension means? There has to move in a straight line. There has to move in a straight line. That means before collision and after collision, there has to move in the same path. Then we can call that one as a collision in one dimension. Okay. Yes. A collision in which the initial and final velocities of two bodies are along the same straight line. Initial and final velocities. That means before collision and after collision, there has to move along the same straight line. Then the collision is said to be one dimension. Now we have to think of elastic collision in one dimension. What is elastic collision? We came to know that the collision in which both the conservation of momentum and kinetic energy takes place. So let us consider the two bodies, that is body of mass m1, which is initially moving with velocity v1i. v1i is initial velocity of first body, and the second body is at rest because v2i is 0. So this body of mass m1, which is moving with velocity v1i, collides the second body of mass m2, which is initially at rest. So this is before collision, and because of collision they are going to exert force on each other, such that after collision also they have to move on the same path. Hence here theta 1 and theta 2, they must become equal to 0. Really collision ಆದ್ಮೇಲೆ ಒಂದು ಪ್ಲೇನ್ ಅಲ್ಲಿ ಹೋಗ್ತಾ ಇದೆ, ಆದರೆ ಅದು ಸಾಧ್ಯ ಇಲ್ಲ. ನಮ್ಮ ಪ್ರಕಾರ theta 1 theta 2 ಎರಡು 0 because it is collision in one dimension. So after collision they may move together like this, or they may move away from each other. That means whatever the motion takes place, it must be along the same straight line after collision also. So let us consider because of the collision, m2 starts to move with some velocity v2 f, that is the final velocity of second body, and the final velocity of first body is m1 f. Please make the things clear. m1 is the mass of the first body, m2 is the mass of the second body, v1i is the initial velocity of m1, v2i is 0, and after collision v1f is the final velocity of the first body and v2f is the final velocity of second body. So the theta 1 theta 2 0 means they are moving in straight line. So now elastic collision, since there is a conservation of momentum, so momentum is nothing but product of mass and velocity. So momentum before collision is m1 v1i plus m2 v2i. Since v2i is 0, just to left with m1 v1i. So momentum before collision is m1 v1i, that is equals to momentum after collision. After collision both m1 and m2 they are going to move with velocities v1f and v2f. Hence the momentum after collision for first body is m1 v1f plus the second body is m2 v2f. Let us call it as equation 1, that is conservation of momentum. So now, in the same way, because of elastic collision, the kinetic energy is also conserved. What is the expression for kinetic energy? We have that kinetic energy is equals to half m v square. So kinetic energy of before collision will be half m1 v1 I square. Half m1 v1 I square. After collision, it is the sum of these two. It is half m1 v1 f square plus half m2 v2 f square. This is the final kinetic energy of first body. This is the final kinetic energy of second body. The total sum after collision will be half m1 v1 f square plus half m2 v2 f square. That is equation number 2. So now we have to get the expressions for the final velocity of the first body and the final velocity of the second body. So by making a small variations in this equation 1 and 2, we have to represent the velocity of first body in terms of the velocity of second body and the velocity of second body in terms of the velocities of first body. It is very simple. Just write the equations and just follow the modifications what we are doing, just mathematical steps, the derivation will be complete. So now, by making a small adjustments, we have to express the velocity of one object in terms of the another object, because we must know the final velocities of the first object as well as the final velocities of the second object, isn't it? So for that, so we have equation number 2. Let us cancel that 1 by 2. Here we can take that 1 by 2 as common. That 1 by 2 will get cancelled with this term. Just we have with m1 v1 I square is equals to m1 v1 f square plus m2 v2 f square. Let us try to get the velocity, final velocity of the second body. So keep this term as it is. Take this m1 v1 f square to that side, it becomes minus. So we are going to have the equation m2 v2 f square is equals to m1 v1 I square minus m1 v1 f square. That equation I have written here. m2 v2 f square is equals to m1 v1 I square minus m1 v1 f square. It just requires our concentration. That's it. Nothing more than that. So now, v2f square we have, just I am writing it as v2f into v2f. So m2 v2f into v2f. It is nothing but m2 v2f square. That is equals to, I am taking m1 as common. So if you take m1 common, what will you have with? So in these two terms, if you are taking m1 common, we just left with v1 I square minus v1 f square. So from equation 1, so here we have equation 1 right. So what we can write for m2 v2f? Here we have m2 v2f. So in order to get m2 v2f, we have to take this m1 v1f to this side. So it will become minus. That means m1 v1i minus m1 v1f. That is nothing but m2 v2f. So by using equation 1, m2 v2f can be written as m1 v1i minus m1 v1f. m2 v2f is equals to m1 v1i minus m1 v1f. So now instead of this m2 v2f, I am going to write m1 v1i minus m1 v1f. What happens now? Instead of this, I am writing m1 v1i minus m1 v1f into v2f is equals to m1 of v1i square minus v1f square. So now, here in both the terms we can take m1 as common. If you take m1 common, what will left with? v1i minus v1f of m1 v2f is equals to m1 of v1i square minus v1f square. This m1 will get cancelled. What we left with now? v1i minus v1f into v2f is equals to a square minus b square means a plus b into a minus. That is v1i plus v1f into v1i minus v1f. And finally we got v2f is equals to v1i plus v1f, because this v1i minus v1f, v1i minus v1f will get cancelled. Just to left with v2f is equals to v1i plus v1f. So by using this, we can get velocity of second body in terms of first body as well as the velocity of first body in terms of second body. Yes. So we got the expression. The final velocity of the second body after collision v2f is equals to v1i plus v1f. So let us make use of this equation in our equation 1. That is, our equation 1 is m1 v1I is equals to m1 v1f plus m2 v2f. So instead of this v2f, let us substitute v1I plus v1f. So using in equation 1, that is v2f in our equation 1 must be replaced by v1I plus v1f, where v2f is the final velocity of the second body after collision, that is equals to v1I plus v1f. That is velocity of first body initially, it is before collision, plus velocity of first body after collision. So our first equation m1 v1I is equals to m1 v1f plus, up to that everything remains same, and here m2 instead of v2f we have to write as v1I plus v1f. Just multiply this, and here we are going to have m2 v1f, m2 v1I. Let us take v1I terms one side, because here we have m1 v1I. If you multiply this m2 with v1I, we are going to have m2 v1I. So I am taking that m2 v1I this side, we are left with m1 v1I minus m2 v1I is equal to the first term m1 v1f as it is plus m2 v1f. Isn't it? So in these two terms we can take v1I as common, we are left with m1 minus m2. That is equals to, here we can take v1f as common, we are left with m1 plus m1. Finally, we are going to get the final velocity of first body, that is the velocity of first body after collision. The expression was that v1f is equals to m1 minus m2 divided by m1 plus m2 into v1I. That means the velocities of the bodies depends on the masses of the objects. So that we are considering the massive object is colliding with light object, or the light object is colliding with the massive object. So everything depends on the masses. So the final velocity of the first body is equals to m1 minus m2 by m1 plus m2 into v1I. This can be obtained by representing final velocity of second body in terms of the velocity of first and initial and final velocity of the first body. Similarly, with just with a small part of the derivation, you have to try this. So by this we can write the final velocity of first body. So v1f is equals to v2f minus v1. So make use of this v1f is equals to v2f minus v1I in our equation 1. So here instead of v1f you have to write v2f minus v1I. So by rearranging you have to get the expression for final velocity of second body. As similar to we got the expression of final velocity of first body right. So just it takes 2-3 minutes. That's it, not more than that, or 2 to 3 steps. Just I am giving the assignment for you, because you have to work out, isn't it? So here we got the final velocity of first body and small modification, that is v1f is equals to v2f minus v1I. Use this in equation 1 and make a small arrangements to get the final velocity of second body, that is v2f is equals to 2m1 by m1 plus m2 into v1I. Okay, this is the elastic collision